last time then, we were really concerned with powers. It's all to do with powers, the laws of indices, what you do if you multiply numbers with the same base, you add the powers, and so on. Following on from these laws of indices to do with powers, we came up with the laws of logarithms. A logarithm is a power of 10. So we turn a number into a power of 10, which means that, again, if I'm multiplying two numbers together with the same base, and in these they must be the same base because it's to the base 10, I add them, So multiplication becomes addition, division becomes subtraction, and the most important one power raised to another becomes a multiplication. So that's what we were focusing on last week. We were using it to solve indicial equations, so we're looking at some examples like this. It's out of the textbook, page 163, is that, or 103? And this was one of the ones in there. So let's just have a look at one of these, just for George, because he was away, and remind ourselves what we were doing. So what's the first step in solving something like this? Take powers of both sides, effectively turn both sides into powers, so we take the logarithms of both sides. We write the logarithm of the left-hand side equals the logarithm of the right-hand side. That's always the first step. If we're interested in the power, if the power is part of the thing that we're trying to solve, whether or not x is the base for it with raised to a particular power, or x is in the power itself, we take logarithms. And the reason why we take logarithms is because of this third law of logarithms, which tells us that the power in here, n, can come down and become a multiplication. That's why we do it. So we go to here, and that means that the x minus 1, which is in the power, can come down and go in front. So we say x minus 1 times the logarithm of 2 equals 2x minus 1 times the logarithm of 3. And if you want to, you can say it on the side because of the third law of logarithms. Okay? At this point, the rest of it is all just to do with solving equations. So this is solving an equation. What we have to do is get all the terms involving x on one side and all the numbers on the other side, so then we can work out what x is, like you would with an equation. The logarithm of 2 is nothing more or less than just a number. If you typed in log 2 into your calculator, you'd get what that number was. And so is log 3. They're only numbers. And so we could multiply out the brackets. But the trouble is, these numbers are quite long, awkward decimal numbers. So what we did to make life easier for ourselves, if you remember from last time, was divide both sides by a logarithm of 3 to get those awkward numbers together. So if I divide both sides by log 3, I get x minus 1 times log 2 over log 3. So I can lump them together into one new number effectively, equals 2x minus 1. I no longer need the bracket. So work out what log 2 divided by log 3 is. And it's equals 2x minus 1. And at this point, we've introduced an approximation because that's been rounded to two significant figures. It's not exactly 0.63. So any value we come up with for x at the end is going to be to two significant figures because we've only got this to two significant figures. So if you want more accuracy than that, you're going to have to quote this number to more accuracy. Okay? That depends on the situation you're in. At this point, we're saying, OK, 0.63 is good enough. So when you come up with your final answer for x, there's no point doing more than two significant figures. Okay, what would we do now with this equation? George is suggesting add 1 to both sides. That's a good idea, but also expand out the brackets before we do that. So multiply out the brackets. 0.63 lots of x minus 1 lot of 0.63 is 2x minus 1. And now what we've got to do is get all the x's on one side and all the numbers on the other side. I've got 0.63 lots of x on this side and 2 lots of x this side. If I subtract 0.63 lots of x from this side, I'll get rid of those x's. But if I do that, I must subtract 0.63 lots of x from this side as well. See that? To keep it balanced. So 2x minus 0.63 lots of x gives me 1.37. So I've got negative 0.63 equals 1.37 x minus 1. I've subtracted the smaller amount of x's from both sides. And now I want to get the number, which is together with the x over the other side, so I add 1 to both sides. Add 1 to this side gets rid of that minus 1, but I must therefore add 1 to this side as well. So I end up with 1 minus 0.63, which is 0.37. And now finally, I've got 1.37 times x, so divide by 1.37. If I divide by 1.37, they cancel. So long as I divide the other side by 1.37, I'm okay. So divide both sides by 1.37, and I get x equals 0.37 over 1.37, which is, say again, sorry. Thank you. So we use these powers and the ideas of logarithms to help us solve problems where x, in this case, is in the power, called an indicial equation, and you'll certainly have 1 or 2 to do in the assignments. We use logs to do it. Another area we use logarithms is in looking at power functions, which is again what we were looking at last week. Before we get onto that, though, a quick review of the equation of the line from last time. Y equals mx plus c should be something that you're familiar with, where if we've got a straight line graph like this, y against x, the gradient of the line is m, and the y-intercept is c. And so that's something we use a lot when we're plotting graphs. Often when we're plotting graphs, we're after a straight line. And if it's not naturally a straight line, we adjust the axes, as we did last time, so we do get a straight line. And then we know that we can find some of the constants in the formula by finding the gradient and the y-intercept. So a bit more on that today, and that's the sort of thing we're leading on to for the assignment. Looking at this, we looked at this power function, plotted these values. If you plot those values directly, you certainly don't get a straight line, because the relationship turns out to be something like this, look. And we've got to prove that it's of that form. So what we do is we use logarithms on this, because one of the things we've got to find is n, which is a power. So as soon as you see powers, you think to yourself logarithms. So what we did was we played around with this function by using logarithms on it and these laws of logarithms, which are, remember, here. If I've got two things multiplied, I add. If I've got one power to another power, I turn that into a multiplier, these two. So if we go back to this, the first thing we do is take the logarithm of both sides. And then we focus on this side here, because I've got r multiplied by I to the power n. So multiplication becomes addition. So I can turn this into the log of r plus the logarithm of I to the n. But again, as we've just been looking at for indicial equations, if I've got I to the n, this power n can come down and become a multiply. So we end up with this equaling the log of r plus n times the log of I. So log p equals that. And then we wrote it round the other way. N log I plus log r. Just swap them round so that, if you remember, we could compare it with this. Now going back to this, to here, prove that the law is of this form, p equals ri to the n. Now we can try and prove it by rearranging this function, p equals ri to the n, and this is a function that relates the power to the current. So we've got power against current in here. If we rearrange that function, and that's what we've done, here it is, it's the same function just written in a different way, i.e. like this. Now if we plot not the power but the logarithm of the power against not the current but the logarithm of the current, and we get a straight line, we've proved that the function is of this form. The fact that we get a straight line means it must be of this form. And more than that, if it is a straight line, finding the gradient of that line tells us the value of n in the function, and the y-intercept tells us a logarithm of the number r in the function. So we can find r and n in this original function here by plotting the graph and finding the gradient and the y-intercept. And that's what the sort of thing we were looking at last week and what you need to do for this assignment I'm going to give you.